average expectation value of the velocity of this electron, it also should stay constant. And its average position should just progress forward with constant velocity. Okay? Reasonable. And since it is a quantum particle, the distribution has width. And we are asking ourselves what will happen to the width. Will it narrow, get broader, or form maybe some patterns? Right? And there is a hypothesis. It will not become sharper. It will not develop patterns. It will just become smoother, which is rather simple. For probability distribution, if you look on the wave function itself, then it will develop some patterns. So everything we are doing today and part of your homework, and we will be working on it next week as well, is only mathematical tools to prove these two hypotheses. Right? And we are doing it because you already know the major principles that help us to answer you know, major principles that allow to predict future, and we passionately want to predict future of molecules and chemical reactions, and maybe some nanostructures. But by now, it will be a little too quick. So we need to go slowly but surely. And one-dimensional planetary space is the good thing to start with. Oh, now I understand why not everyone came, thinking that if not present, that's a meaning.
I think Morgan's.
And if you are busy with other responsibilities or do not feel well, or just not in a good mood to travel to the campus, send homeworks by scan email, and we do have.
I will add.
Yeah, just do.
I have my homework finished, and I will bring it to your office this afternoon.
Whatever,
if that's okay.
Whatever is comfortable, you can just scan and send electronically.
Okay, I can do that too.
But I will be happy to see you. But if it is the only reason for you to travel, then you do not need to.
But thank you.
When it will be more complicated homeworks, we will make a review session and keys, but this is rather simple. Okay. And maybe this one will need a little review session. Does it look possible to make some progress towards Monday? Let's try. Oh, it is an answer. I shouldn't show it. It is what you should have in your quiz. So you do know Schrödinger equation, time dependent. You do know concept of eigenvalues, and you already know that plane wave, which is just exponential with the power of imaginary unit momentum and position, divided with like constant to have dimensionless, will be an eigenfunction of the momentum operator. And since power, algebraic power, any algebraic power of operator will have the same set of functions as its eigenfunction, the momentum square will have this, anything that was eigenfunction for momentum will be also eigenfunction for momentum squared. And Hamiltonian in free space is momentum squared with some constant. Through this simple logic, which not will be possible for the rest of the problems. The plane waves are general solutions of Schrödinger equation for electron in free space. And we are going to construct, those are just some ugly writings in support of what we are telling. So we are going to practice the prescription in the third way to predict future, since we do want to predict the time evolution of the initial Gaussian wave packet of electron, wave packet that electron that is localized in a certain area of space, certain probability, and we are going to see how to evolve further in space to check our hypothetical answers. If we want to practice the third way of predicting future, we need three things, and basically they are let as empty boxes in your quiz. Right? So we do need eigen functions of the Hamiltonian solutions of time independent Schrödinger equation. And you already know those are just variables. So you can fill the first box right away. E to the power I p x divided by h bar. The second box will be evolution. So when we were starting to speak about Schrödinger equation and its solution, we were making an effort to separate variables. When we were building a split of Schrödinger equation onto time dependence and spatial dependence, we agreed that time dependence will be always an exponential with energy of a given state in the power of this exponential. So I know that you deserve much better calligraphy. So it will be minus I over h bar, energy of this, the index should be the same. It is eigenstate phi sub k, this will be an eigen energy E sub k. Oh, nice to meet you. How are you? Good. Any homework for me? Fair trade. To please you, there is a little quiz. But it's not special for you, it's for everyone. Thank you much. So we will show, or you can see it immediately, that the energy of the plane wave will be momentum squared. I would be happy to choke the sentence on little items, prove that you may already see. Because kinetic energy is momentum squared over 2m, right? And if we have the k is momentum divided by time, either put momentum here or this k stuff, which is equal to momentum with precision up to this part. So it will be energy of each plane wave. And the only thing that we do not know is expansion coefficient, the fraction, the percentage with which general solution contributes to partial. So it should be so many percent of plane wave with velocity 1, so many percent of plane wave with velocity -1, and infinite series or integration over all plane waves. But this percentage will depend on momentum or on the wave vector. Why this wave vector is here?
What does it say in the top right corner? Sorry,
Top right corner?
yeah, I don't know it.
It tells enjoy the beautiful calligraphy. It is, you know, the top right corner probably everyone tries to write here, and it is this touch screen is untouchable. I'll put it maybe E I K X, and if you define P over H bar as P, same as E I P X over H bar. So for your surprise quizzes that I will be collecting at the end of the meeting, you can always already fill the first two boxes. And I will not tell anyone that you are doing it during the class. Simply do it class. But the only unknown box is C sub K. So how do we find it? We are not going to practice anything new. We already know the prescription. So we take the Gaussian function, multiply it by wave and integrate. And since we are going to integrate it over position, the result will depend on momentum or this A, A. Just in case if you are not yet convinced about the energy, that it will be H bar squared K squared over 2m, you can plug in the eigenfunction into static time-independent Schrödinger equation and just see what happens. So we need to find out what will happen. So if we apply first derivative to get IP, if we apply another derivative then it will be minus I K minus I K E. And there's my mistake that no. There was two quotients. So minus times minus will be plus, I times I will be negative 1. So we'll get minus K squared E, and then favorite calligraphy of always. I'm a little better. So we did practice second derivative, but this so if we put H phi, right, then it will be minus H bar over 2m minus K squared phi, because our phi was defined this way. And then everything that is placed in front of phi, so minus will cancel, will be the energy of the state. So in some sense, we did solve the eigenvalue problem for plane wave. I'm not sure if you should brag and tell everyone about this heroic feat, because it is much simpler than the rest of eigenvalue problems. The formula is E sub A equals this stuff. So just your second box in surprise. So in some sense, this split of momentum into wave vector and time constant is made to split, to factorize derivative over position and time constant. Just some people it's considered more convenient. I think they're doing this little exercise all the time. We are progressing through slides really quick. So the next question is to find this CSAP. And I don't remember if we are finding it today or I just want to. I'm a little messed up with timing of the homeworks. If the homework 2 would be done by now, the answer from the homework 2 will be input for today's lecture. But when you do it at home, you will see here's no entry, everything is too open. This is answer for your question number 3 in homework 2 that you hopefully will bring on Monday. So let's just discuss what it is, and then you practice a little bit of math. So when we setting up initial condition localized in space, it is Gaussian function, and right now we are skipping pre-normalization prefactors. If we are doing work for higher, we cannot do it. Right now, for principles and proofs of concept, let's save 5 minutes here and there. So the width of this Gaussian bell is in the denominator of the power. The larger the sigma, the wider the Gaussian bell. The narrower, the smaller the sigma, the narrower the bell. So a little discovery that everyone who will practice homework 2 number 3 will do is that the answer will also have Gaussian function. But it will be Gaussian function as with independent variable being k instead of x. So C sub k depends only on the wavelet. And the meaning of this solution is that it gives proportion. So if we place plane waves with different momentum, with different momentum means density of fringes. Big velocity, frequent fringes. Small velocity, very sparse fringes. And then suppose that we have arsenal of plane waves. Here I have long waves, here I have short waves. And now I'm trying mixing them to cook the wave pattern. And here are proportions of my ingredient. So I should take most amount of the long waves, a little less mid waves, both going positive and negative, and very few waves that have small wavelengths and very high momentum. So it will be recipe how to construct space wave packet out of momentum, out of plane waves. So it's maximum at k equals 0, and then as we go away, it will be less and less. Same dosage. But what is interesting, and it is one of the mathematical features. Typically, I hate all these little details, but sometimes one needs to focus here. So here, the width was located in the denominator of the power. if we carefully do this homework 2 round 3, the width will pop up in the denominator. And it will mean, to some extent, the inverse relations. So the wide wave packet in normal space will correspond to very narrow wave packet in momentum space. So the recipe will become very simple. Only if the width is absolute 0, it means only one wave packet. If our wave packet in normal Cartesian spatial space is very narrow, if our electron is localized at a specific point and nowhere else, then in momentum space it will be very broad. It will be constructed all possible plane waves always in equal measure. Right now we need nothing more. It's only mathematical observation, but a couple of weeks later there will be a serious philosophical concept, so-called uncertainty principle, that one cannot measure simultaneously the position of the matter. And this little mathematical observation is a reflection of this principle. You just see this reflection before we study this principle. So, is it the whole story? Can we celebrate and go party and consider this problem solved? No. Why? So what do you see on your quiz? You have 3 boxes on the right. On the left you have wave function of the future, right? And what do you have right after the equal sign? And then next? Integral over which variable? Yes. What does it mean? Oh, I have the same here. So that we need to add together or integrate over all of these plane waves with different coefficients, right? So we plug in this C sub k coordinates. Oh, no. Here we integrate over dx and you get a function of k. And now I'm doing everything correctly. And in order to predict future, we need to integrate over k and get dependence over x. I told it correctly. But if you doubt, I can.
Why is it a coefficient if k is in the function?
I do not know how to explain it in a good wording, but I have a very clear sense of it. So if we play with natural numbers, if you count apples, there is like 1, 2, 3, they are integer. But if we measure toothpaste, it's continuous. So we use index at the bottom as it would be for discrete objects. But no one forbids us to have a plane wave with momentum in between these 2 discrete values. So in some sense, values of momentum are continuous. You can consider plane wave of any possible velocity, any possible momentum. Therefore, it would be much more correct, instead of this notation, tell it is C as a continuous function of k. And then we need to integrate over it. It's a perfect question. I was fearing and trying to avoid this discussion, but thank you for bringing me out of comfort zone. Make sense? What's that? It's a little surprise for me. So this is fast, this is the expansion coefficients, and we do need to make gray. It looks like repeating. Okay, good. I have my brain cell the recipes. So 3 boxes, and if I would avoid the question from Alyssa, I would keep writing summation. But after our comparison between apples and toothpaste, we can replace summation with integral. So just exponential, which depends on both. And I cannot teach myself. I always using the word momentum instead of wave vector, but k is wave vector, p is momentum, and they are different just by factor. So k and x, wave vector, which is almost momentum in position. Here is just time factor, but since we are making summation or whatever, integration or summation will be replaced by dk from minus plus infinity. Since this is factor that depends on time, but since we are integrating over momentum, this integration will depend on this factor as well. And of course, it will depend much on this exponential factor. So as soon as we multiply these 3 things and take integral, the answer will be our future. Not so scary, not our future, but future of electron in free space. Our future is more colorful. And here we do have a challenge that actually, in fact, it shouldn't be our business. It's a mathematical problem that we should be able to solve either ourselves or by hiring a professional mathematician or by running a pool. But for learning purposes, we'll, at the beginning of the course, we'll try to solve few problems ourselves. But this is just a little exercise which is a little separated from major goal. Major goal is to get understanding of principles and being able to interpret experiments, but through doing it manually by hand, level of understanding may increase. So, I invite you to do this with understanding that to some extent math is secondary to basic principle of science. But if we agree to do this little torturing exercise, then what do we see? What is common about all 3 boxes? Yes, exponentials. And product of exponentials is exponential of some of their powers. Right? So basically, it will be integral of an exponential, which is probably okay. But before, we were living an easy life, and we were integrating exponentials where powers were linear in the independent variable, right? We were integrating stuff like that, which is linear either in k or x. And now, after we add together these powers, it will be exponential that has a polynomial x plus k squared, k plus k squared. And so in some sense, we need to take integral of e k squared dq. Do you know the answer from the book? Huh? Is there answer for this indefinite integral? Some mathematical problems do not have answer. So if it is an indefinite integral without limits, there is no answer in normal functions. There is a special function which is just called error function. But generally, there is no answer. There is a specific answer only in our lucky case when there are limits. And basically the meaning of such, well, we will connect this complicated integral with the simple one. The meaning of this integral is area under Gaussian curve. Now I'll ask once again. What is the area under Gaussian curve?
What?
Huh?
I don't know. What?
Very close. Well, it will be constant, right? And it probably will be one of the famous numbers. There are not so many. Yes. Good. Super. So our goal is just maybe square root of pi. But we can prove it, and then by, I don't know how frequently you do integration and how much you like it, how much you dislike it, but there are little tricks that if you do it frequently, you forget about where they come from. If you do not do it, you just hate them. And I came to them only when I needed to instruct and verbalize. Like the best integration when integration variable doesn't have factors. Right? And in order to avoid factors, one can multiply the integration variable by some factor and divide by the same factor the whole integral. Multiply and divide by some. Then, if we will have a polynomial, exponential polynomial, we can redefine new variable. The all polynomial will be a new variable, which means we travel in the space of variables just by shifting the origin. And doing a couple of these little things simplifies overall procedure. So it's less writing, more thinking. Or sometimes there is a big temptation to just close eyes. So this is Alice's question. Limit of if we go from discrete to continuous limit, if delta k goes to 0, then it is the equation from apples. So here is probably it was unfair quiz, and it is good that I distributed because to fill the last box we need the completed homework.
Is it H bar or is that pi?
Where? Oh, I have a fan club of my calligraphy. It's square root of pi times sigma naught.
On one of the previous slides, we had the exponential of negative k squared sigma naught.
Yes.
over 4. Is that still
If it is if sigma naught is not here, it's my fault of being not careful. But sigma naught is there. Yes. Yes. Extra point. Okay. So I'm not sure if you will take this integral today together, but I will sketch the principles how to take it, because in your homework you will need these principles. So those are your three boxes: first, second, and third. Then we add powers of all these three exponentials. And what I suggest to do, just as the favor to my own laziness, maybe someone is on the same page as me. If one tries to solve and write, like this one was maybe one page, but if you try to do integrals like that, it may take several pages. And most of the time it will be just repeating the line that changes just a little bit. So why don't we avoid unnecessary writing and redefine some combinations of variables in a simple way. For example, everything that stands in front of k squared, with the second power variable, we will call it b. Everything that stands in front of the first variable of the independent variable, we will call a. And then we will just record and anything that is away from exponential will be c. Then we need to take integral that looks a little more condensed, because these coefficients will be not affected by integration. We don't care what they are when we are like, if we are not physical chemists but mathematicians, if someone hires us to take this integral. We don't care how things change with time or position. For this integral over dk, we are interested only on the dependence on this integration variable. Right? And if you are busy or lazy, or like have some other, if your schedule is overloaded, or if you need a backup solution, though integrals like this are in PTP and online, there are in books of tables. Before all computers, people were solving integrals and tabulating them in books. So in some sense, we just need to pick up this integral, the result of this integration, plug in this variables and report solution. For educational purposes, we can practice it a little. And it will be really helpful for like development of mathematical muscles. But global use of this experiment will be not as strong because many people did it before. Okay. You have a few questions?
Yeah, are sigma and delta the same?
Sigma and delta?
Yeah. So.
Oh! It's a fun club of calligraphy. There's because Latin alphabet is too short and there are so many new concepts in science, people use Greek alphabet.
Yeah. Which
are just little different symbols for the same sound, right? So there is an analogy. And it's much easier than well, instead of C is not analog, but then for D they have delta, which looks this way, and further away in the alphabet, the letter S is in Greek alphabet like sigma. So sigma and delta are different. Delta is like D, and sigma is like S.
So in this case, are they interchangeable, or did you just?
They're not interchangeable. Scientifically, they're used for different purposes.
So, I think the question is, what is sigma?
Sigma in this equation is the width of the initial wave vector.
Okay, then what was delta in the previous?
Delta was like 2-3 lectures ago for snake eating the rabbit.
It was on the previous slides.
I accept being guilty for calligraphy. But
oh, so that's supposed to be sigma. Sigma,
no delta. So sigma goes tail up, delta goes tail down. I don't know how to explain it, but it looks like little O and then a tail, but here is only one inflection, and here there are 2 inflections, like up and down. So let me. If you hate internet and books of integrals, which I doubt, I can just sketch direction of solution. When we meet on Monday, I probably will solve these integrals myself as demonstration. So I like this just as an elegant solution, although no one needs it. So assume that we have two-dimensional space, x and y. In each of directions, we have the same integral. So it's Mexican sombrero. Okay. And then we multiply integral over x and over y. Then it will be two-dimensional integral, dx dy. Then we can go into two-dimensional space. X squared plus y squared will be distance squared. And here we have dx dy is just small area increment. And if we go into polar coordinates, the small increment of space will be r dr d phi. Right? So I don't know, maybe it is on the next slide. R dr d phi. And if you have e to the power minus r squared r dr d phi, then one can practice integration by parts. So if it is only Gaussian function, it is not integrable. But if you have r here, because of this two-dimension, it's easy to go. And then one unrolls it back and takes square root of it. And therefore it will be square root of pi. Yeah, r dr d phi. Integral of phi is trivial. Redefine new variable r squared equals u, and then integral of this u from 0 to infinity will be so the pi comes from integration of a circle defect. Okay, done. It's and I will just give some hint. And I intend to send the slides so that you can watch through it. I am really touched by you taking notes. It's very pleasant to my heart. But I will send this. Okay, meeting is done. Thanks much for investing your time.